So my name is Lyublena. I'm a software engineer at Meta. I'm actually subbing in for Pranjal, who was supposed to give this talk, but he's out sick. And the beautiful slides you see were mostly done by him. If you see something ugly, it was probably done by me. So I'm going to talk about history-based optimization in Presto. And I'll first start by motivating query optimizers in general. You might have heard a few talks today that talk about that. So most of it shouldn't be news. But then I'll go into the architecture of how we built this HBO thing. And namely, how do we quickly look up histories for plans that were executed before? Where do we store statistics? How do we design that? And then kind of the more important part is how do we use that in query optimization to make the query run better. I'll present some results. So we've been running with HBO in production at Meta for probably a year now. So I have some results to share on how that looks. And I'll give ideas of where we want to take this project in the future. So if you've ever touched a database engine, you probably saw a version of that chart, that diagram, and you probably saw it a couple of times throughout the day in various presentations. So this is the life of a query when it hits a database engine, and that looks similar in all database engines. It starts by the client sending usually a SQL query, which gets parsed and analyzed into some sort of abstract syntax tree. And then the role of the query planner or query optimizer is to take that query and produce an efficient query plan that is then sent to the workers for execution. And that's depicted here in this red box in the middle. So that's kind of where HBO lives. That's the component that we'll be modifying to make that work. Here, a simple example. That's a join query that joins two tables, T1 and T2. And again, I know that there were a couple of examples like that all day. It is the job of the query optimizer to decide which join order to pick. Is it better to join T1 with T2 or T2 with T1? And that decision usually cannot be made in isolation. You need some statistics, some data to guide you to pick what is better for evaluation. If it's a hash join, you typically try to evaluate the or build the hash on the smaller side. And what is the smaller side is the kind of the tricky thing that you have to consider. I don't know, my presentation looks much better. So that's what we call cost-based optimization, kind of having this cost oracle that guides us through deciding what plan shape is better for query evaluation. The classic cost-based optimization typically stores some kind of base table statistics. We have those in Presto. Those look something like, for each partition of the data, we store how many rows there are. And then for the columns, we can store additional information like what is the number of distinct values, what are the number of null values in that column, what is the size of that column. But that's only at kind of the leaf nodes of the query plans, where you can expect to get somewhat precise data. When you're optimizing a query, there's typically various operations that get applied, like filters, projections, aggregations, and so on. And when you start deriving the statistics at intermediate nodes, it all of a sudden starts losing accuracy because you're trying to approximate something with incomplete data. You're trying to approximate what the selectivity of a filter is when you don't really know what the data distribution is in this case. And there's more sophisticated way to model data distribution. That's currently not part of Presto. So the best you can do in this case is if you have a filter that says status equals done, that's like an equality predicate. You have the number of distinct values, so you can try to say, okay, if distribution is uniform, that's how many rows I'll get once I evaluate this predicate. And of course, if data is skewed, that's going to give you incorrect estimation of the result. But that's still better than nothing in most cases. So again, estimating statistics is error prone because you have incomplete data and because the complexity of the query is usually higher than what your model covers. You have complex predicates that aren't just equality. They're usually range predicates. They involve case expressions. They involve lambda expressions. They involve all sorts of things. And if you try to estimate the kind of the cardinality after applying this predicate, it quickly gets into something that you cannot really trust. And most queries are not written by hand. Most queries are produced by tools such as dashboards or pipelines that are run every day. So that kind of makes this approach somewhat limited. So what we decided to do instead is kind of turn into this kind of historical-based statistics. Because one of the observations is that we do have a ton of queries that come from the same template that are run on a daily or hourly basis. These may be dashboard queries. This could be kind of batch jobs that just take the new daily partition and turn it into whatever other daily partition in the other table in the pipeline. So because we've seen kind of the query plan the day before, what if we can take these statistics and plug it the next time a similar query comes around? And that will give us a much better kind of idea of these intermediate cardinalities. And we should be able to make a better decision of how to optimize such a query. I don't know what's happening with my slides. So yeah, again, the idea is when a query runs, you extract the histories and you store it in some sort of stat store. And the next time a similar query comes around, you use that information. And this is kind of the architecture of how this looks like. So on the left, it's kind of the same diagram that you saw at the beginning of this presentation, which shows the life cycle of a query. We only added this one last box at the end, which says, once I'm done executing the query, I'm going to look at the results and the statistics from that execution trace, and I'm going to store them in a stat store. So that's kind of the right path where you have your trace, you update your stat store. I'm a little vague about how we do that, and I'll cover some more detail in the future. So now the question is, once we have that, how do we use that information kind of in the important read path of HBO? So here in the middle, I've zoomed in into what kind of the query optimizer looks like. Like Ryan said a couple of presentations ago, Presto optimizer is a rule-based optimizer where we have a bunch of 100-something rules. Each one of them is applied to the input query, produces a new one, a new plan, and so on and so forth. And once we have refined it, using all the rules, we send that for execution. So what we did was we had this sort of in the middle, not in the middle, but after we apply kind of all the things that we think we should be applying, we have a historical optimizer. And what it does is again, we're trying to find similar plans. It's not going to be exactly the same query, but it's probably going to be a very similar query that came from the same template. And the goal of the historical plan is to do two things. One is to compute this canonical plan, where you ignore stuff that might have been different yesterday. And the second point is to go to the stat store and fetch if you have any traces for a query that looks like that. And that's kind of this read path all the way to the right to the start store. We have a local stats cache so that if we have to do multiple round trips for the same type of statistics, we store them locally for the query. So once you're done fetching these statistical traces, all the other optimizers, I've called them CBO, so these are cost-based optimizers, can now take advantage of the statistics that we fetched from the stat store and can make better cost-based decision on how to proceed with the query plan. So to the interesting part, I said a couple of times we want to be able to find not necessarily the same query, but a similar query for which we have an execution trace. The assumption here is that, yes, if we ran yesterday a query that looks for data from January 1st, maybe tomorrow we'll run the same query that looks for data for January 2nd. And that's one. And the other thing is we don't want to have to compare plans node by node because that's going to be expensive. If you have to search through millions and billions of query plans, performing an operation like that would be kind of expensive and prohibitive. So you want to be able to somehow hash that information so that you can quickly look up, do I have stats for a plan that look like this, or do I not have stats? So the second part is hashing, and I'm going to cover the two of them in the next two slides. So the first part is kind of computing this template or canonical plan. We make the assumption that partitions are kind of the same, have kind of the same data and data distribution, and that doesn't change like super rapidly day over day. If it does, we'll cover it and we'll kind of take that into account in the next iteration. But between kind of today and yesterday, things should look the same. And when I say today and yesterday, I mean this run and the previous run. It might be hourly, so it could be an hourly difference. So when we want to compute the canonical version of that plan, we're just going to ignore filters, especially quality filters that look at date constants, or partition key constants, I should say. This fits really well if you have scheduled pipelines, because they typically just change kind of this literal in your query, but keep the rest the same. We have some refinements where we try to also remove other literals of the query. Obviously, that is kind of more prone to errors because data distribution for different values may be different if that's not the partition key. But anyways, with these kind of refinements, I think we cover about 95% of the cases where we find the queries that are similar. The next point that I mentioned is that we don't want to be doing node-by-node comparison when we look for query plans. We want to be able to hash that. And for that, again, we make a couple of assumptions, and we treat, for example, if you have a join and you executed that join yesterday, whether you flip the sides of the join, especially for inner join, that wouldn't change the cardinality of the result. It might change the cost, but if you're just concerned about cardinalities and data distribution and things like this, you can kind of sort the nodes and put that into your canonical representation that you use for hashing. Same with various other things, like the order of columns in a project shouldn't matter, the order of inputs of the union shouldn't matter, and things like this. And that hashing kind of allows you to do these quick lookups in the stat store. So the stat store is nothing other than a key value store where you keep the hash that you can compute it, and you map that to the statistics you acquired for that kind of sub-plan. The statistic includes things like cardinality, or number of rows that you've seen, number of bytes. We started adding various other properties like number of null values and things like this that are helpful for some particular optimizations, but it's typically a few bytes of data per kind of node in the query. So this is all abstracted as an interface, and we have various implementations. At Meta, we use our own key value store. Jay, who is here, recently added a Redis connector, so now it's available kind of for use outside of Meta. And we also have an in-memory implementation that's really good for testing because you can just plug it in and test your optimizers without having to connect to an external key value store. We store the stats in a thrift struct to just make it serializable. And just operationally, we typically keep the last few runs of data, and we can do stuff like average over those runs, and we can kind of age out stuff that's no longer accessed, because if there's a query that stopped being run, you can just throw away the stats that you have from that query. So today, I did that kind of snapshot 2 days ago. I think we use HBO, or we've integrated HBO in 6 different optimizers inside of Presto. I'm going to spend my time talking about the first 2. These are kind of the most important ones, the ones that give us the biggest buck for, what was the expression? Anyways. And these have to do with joins and with aggregations. So the first one is determining join distribution type. If you have a join, you can typically evaluate it in 2 different strategies. One is the broadcast join. If your inner side is small enough, you can just broadcast it to all the worker nodes. And that is we found out that about 28% of queries have that case where the inner side is small enough to be broadcastable. And again, if you have statistics of these cardinalities from previous traces, you can make a much more informed decision of whether that's a good strategy or not. Because if you're wrong, you suddenly end up broadcasting a really large table. But HBO can help us avoid that situation. The other optimization that's important in our workloads is this detection of redundant partial aggregates. So normally if you do an aggregation and you have an exchange node, you try to kind of pre-aggregate data close to the data source before you send it over the network. That works really well if your aggregate is cardinality reducing because you end up sending much less data to the next node. But that's sometimes not the case. Sometimes you're aggregating stuff that's almost kind of distinct. And adding this additional aggregation step can both kind of incur more CPU cost as well as can send additional data over the network because you're keeping some hashes around that that you need to send around. And with kind of HBO, we can detect whether an aggregate is cardinality reducing or not and decide whether to apply this transformation or not. And we found out that about 35% of the queries in Meta can kind of benefit from this type of optimization. Oops. So this is a chart I stole from our SIGMOD paper earlier this year. What it does is it compares what happened if we turn on HBO versus if we use the kind of the classic CBO based on estimates. A value of 1 means the query didn't change, so it's a ratio. So query with HBO ran the same way as query without HBO. So you want to see more kind of to the left of the one where query is actually improved by turning on HBO, and that's kind of what we saw. I think across the board we saw an average of 7% improvements, and there's some query buckets that improved even more than that. So in terms of future work, we do have more optimizers that we can try to integrate. I'm sorry. I was home alone with the kids last week, and that's what it did to me. So we have more optimizers that can benefit from HBO, and we are slowly kind of churning through the list. The other one is that we are currently only looking at successful query runs to get statistics. But what if you have a query that failed because of an out-of-memory exception or something? It probably was because of a bad query plan. So why don't we take advantage of kind of the complete stages, get the statistics for those because we know these are accurate, and try to plug that into our stat store so that it can help find a better plan next time around. And the other thing that we've been looking at is we mostly focused on batch workloads because these are the long-running, repetitive queries. And we recently started investigating HBO for interactive dashboard-like workloads. I want to thank Pranjal and Feilong, who is here, who are the main driving forces behind this project, and also Jay from Uber for contributing to the Redis connector. Thank you.
So basically, from what I understood for HBO, you will have to store a key value in your HBO store, and the key will be the query hash, and the value will be some fifth structure. So would that fifth structure and its contents be the same regardless of where you want to use the HBO optimizer, or would that change?
It is the same. Thrift allows you to have optional fields. So you may decide to populate certain things that matter versus certain things that don't matter. We use that, for example, we store some join-based statistics that only matter if the join was a join node, or aggregation-based statistics that only matter if, for aggregation nodes. For other nodes, it will be an optional field.
So is there any CPU cost that you have seen for this to compute and HPU stats?
To answer, so the writing of stats is done in a parallel thread, so it doesn't affect the main execution. Some of the reading obviously has to fetch stats, and that introduces some latency. We're constantly working on improving that latency, and that's why we first focus on batch workloads, because if it's, your job takes an hour, spending a few milliseconds of fetching stats doesn't really hurt. But yes, if you try to turn it on for dashboards that are supposed to be instantaneous, then you might see some latency for these short-running queries, and that's why we have caching, that's why we use other tricks, but yes, it is a valid point.
My question is related to fragment result cache, because you spoke about the canonical plan and computing the hash. When you see that there is a similar subquery at the leaf state that was run before, the result is cached into the fragment result cache and you happen to reuse it. So I was just wondering, this only helps PPCH queries. When we tried to turn it on PPCDS, we didn't see much of a benefit. So are you planning to extend the fragment result cache in such a way that it doesn't just cover the leaf fragment, but something bigger than that, so that when you see a larger subquery, you can just replace it directly with the result?
That's a good question. I think some other people might be more qualified to answer. So we're working on, and when I say we, I mean Jay, is working on common table expression optimization that basically detects, I think the first iteration will detect if you have a with clause. That's definitely something that can be materialized across the board. So it's more of a, I think it uses maybe the fragment cache to some extent, but can also be abstracted away. I mean, in my talk, I mostly talked about optimization at the level of producing a plan, but not really detecting if what you're talking about is using a result cache where you have computed the results and now you try to reuse them throughout the query. And that, I think, will be done with that kind of common table expression optimization. That's not covered here. That's not part of this.
So the stats which you're storing during the execution of the query, that is being extracted directly from the plan?
Yeah, from the worker nodes.
Maybe I have a question, right?
These are the actual execution stats. They're not the estimated stats from the planner, from the optimizer.
So how do you get the actual, maybe a dumb question I will ask, but the actual values, like how many distinct values are calculated for this fragment?
Yeah, so we have something, a query info listener, and that's kind of part of the package that gets sent to the coordinator, which contains these stats.